Okay, now we are going to finish what we've started on the previous lesson. That was the first part of a lesson that was focused on introducing the Euler angles. And well, on that lesson, we got to this matrix that we have here. Remember that this matrix represents the product between A dot transpose times A. And another thing that we mentioned on that first part is that, well, there's an equation that relates, well, the transpose and the other matrix, well, the regular matrix, with the components of the angular velocity vector with this relation over here. So with the help of this equation, we are going to establish a matrix that will be equal to this matrix that we found here. So if you see, well, these components of the angular velocity are multiplying the Levi-Civita symbol. Okay? And we know that, well, the vector of angular velocity has only three components. It will be omega 1, omega 2, omega 3. These are prime coordinates. And, well, that means that, well, those indices correspond to that S that we have here. And in this case, well, this I and the J of the Levi-Civita symbol are going to correspond to the row for the I and the column for the J of that matrix that we want to write. So for example, let me put that matrix here like this, and for example this is for the position 1, 1, because it's the first row and the first column. So that means that here in the Levi-Civita symbol we are going to have an element, well, the indices 1, 1 for that position. But we know that the Levi-Civita symbol, well, if it has two repeated indices, like in this case, well, it is going to be equal to 0. Okay? Doesn't matter what index we have here for the S, that doesn't matter. We know that the Levi-Civita symbol is going to be 0, so everything is going to be equal to 0. So that means that this first element for this position is going to be equal to 0. And that is also going to happen with the elements that have the row 2 and column 2. So that means that this element is also going to be 0, and it will happen the same with the 3 and 3 indices here. So of course this is also going to be equal to 0. So for this element that we have here, what are we going to get? Well, it is the first column, so we will have a 1 here. It is the second, sorry, it is the first row, yep, and the second column, okay? So we have something like this. So what is going to be the next index in the Levi-Civita symbol? Of course, it will have to match with the index of the omega. And we know that for this to be different from 0, what we need is a 3 over here. Because if we put a 1 or a 2, again, this Levi-Civita symbol will be 0, because we have a repeated index. So we need this index to be different from the other two indices that we have here. So that means that this is going to be a 3, and we will have omega 3 prime, like this. And we know that in this order, looking that this is an even permutation of the sequence 1, 2, 3, and I mean that is an even permutation because we are making 0 permutations. We already have the 1, 2, 3. So we do not have to make any permutation to get to this 1, 2, 3 that we have here. So that means we are making an odd permutation, and that means that the value of this Levi-Civita symbol is going to be just 1. Perfect. So that means that this is just going to be omega 3 prime, and like I said, this corresponds to the element in the first column and the first row and the second column, so this will be omega 3 prime. Perfect. What happens, for example, with this element that we have here is going to be very similar, because in that case we are on the second row and the first column, and for this to be different from 0, this needs to be the number 3, so that means that the angular velocity is going to be omega 3. And here, in this case, if we have the sequence 1, 2, 3, we just need to make one step to get to the sequence. So looking that we need to make one step, and that one is an odd number, that means that this is going to be equal to negative 1. Remember, 2, 1, 3 is an odd permutation of 1, 2, 3. So that means that the Levi-Civita symbol is equal to negative 1, and that means that this is going to be minus omega 3 prime. So here we are going to get minus omega 3 prime. So I hope you understand now the logic of how to fill this matrix. So what happens with this term that we have here? Well, we are located in the first row, the third column, so that means that this element needs to be a 2 to be different from 0. Then this will be omega 2 prime, of course. And here, if we have 1, 2, 3, what do we need to do to get to the sequence that we have here? Well, we need to switch these 2 here and these 3 here. So that means that we need to make an odd permutation, because that is only one change. So looking that we are making an odd permutation, this Levi-Civita symbol is going to be equal to negative 1, and this is going to be minus omega 2 prime. So here we are going to get minus omega 2 prime. Okay, something very similar is going to happen with this element, because we are changing the number of the row for the number of the column. In this case we are in the row 1, column 3. In this case we are in the row 3 and column 1. So that means that the only thing that is going to change is the sign of this omega 2 prime. Okay, and as you can expect, these elements that are left, well, they are going to correspond to minus omega 1 and and plus omega 1. So what is this going to be? Well, for example, for this we are going to get that we are in the third row, the second column, and of course the omega 1 element. So if we have the sequence 1, 2, 3, what do we need to do to get to 3, 2, 1? Well, we change this 3 to this position, we take the 1 to this position, so that means that's only one step. One permutation, I mean. So that means that we have another permutation, so this is going to be minus 1, and this is going to be minus omega 1 prime. So that means that this element is going to be minus omega 1 prime, and this, of course, is going to be omega 1 prime. Perfect. So this matrix that we just found, again, is equivalent to this, which is equal to this. And this in matrix representation is, of course, this what we have. But we have just calculated this product in the first lesson in terms of the Euler angles phi, theta, and gamma. So we can make these two matrices to be equal to get the next equation. Okay, well, this is the equation that we get if we set these two matrices to be equal. Remember that here in this matrix that we found on the first lesson, well, this element corresponds to the negative of this element, which is the same thing that happens in this matrix. We have this element to be the negative of this one. So, well, it happens on on every element of this matrix. So that means that we can establish the next three equations. We have that omega 1 prime is equal to phi dot sine theta sine gamma plus theta dot cosine gamma. Omega 2 prime is equal to phi dot sine theta cosine gamma minus theta dot sine gamma. And omega 3 prime is going to be equal to, well, it will be phi dot cosine theta plus gamma dot. Remember that these are the components of the angular velocity with respect to the axes that are fixed to the rigid body, and here they are in terms of the Euler angles. Okay, perfect. So now we are interested in finding the inertia tensor in terms of, well, the kinetic energy in terms of the inertia tensor and these angular velocities. And remember, there was a video that we made where we calculated the kinetic energy in terms of the inertia tensor, and we got to the formula that says that the kinetic energy is equal to 1/2 the inertia tensor j k omega j omega k. Okay, so to explain this next step, what we are going to do is to consider that the inertia tensor can be represented with a matrix that is a diagonal matrix. Remember that if we choose the coordinate system in appropriate way, we can establish an inertia tensor whose matrix representation is a diagonal matrix. So that can be done if we choose a specific coordinate system. Okay, so if we do that, we are going to call the element I11 of that matrix to be equal to I1. The I22 is going to be just the I2, and the I33 is going to be, of course, I3. So what are we going to get if we do that? Looking at the only elements that are different from 0 in the matrix representation of the inertia tensor are these elements, I11, I22, and I33, we are going to get in this sum that the only elements that are going to survive are the I11, omega 1, omega 1, and then plus I22, omega 2, omega 2, and then I33, omega 3, omega 3. Okay, so we are going to get that this is 1/2 I11, which is just I1, times omega 1, omega 1. Because remember, if these indices are 1, 1, looking at the j index of the omega has to match with the first index of the I, well, it has to be omega 1. And this k also needs to match with the second index of the j, which is also 1. So that means we have omega 1, omega 1. So we get here omega 1 prime squared. And it will happen the same with these two other elements. So we are going to get this thing that I just wrote. Okay, perfect. So what happens if we substitute the values of omega 1, omega 2, and omega 3? We are going to get that the kinetic energy is going to be equal to 1/2 I1, that is going to multiply. It will be phi dot sine theta sine gamma plus theta dot cosine gamma squared plus I2 phi dot sine theta cosine gamma minus theta dot sine gamma squared, and then plus I3 phi dot cosine theta plus gamma dot squared. Okay, perfect. Remember also that when we have the matrix representation of the inertia tensor, and that corresponds to a diagonal matrix, the elements of the diagonal entries correspond to something that we called as the principal moments of inertia. So in this case, that will be these elements that we have here. These are the principal moments of inertia of that inertia tensor. So in this example, it will be convenient to choose the axis in such a way that the principal moments of inertia I1 and I2 will be equal. Okay, we are going to select the axis such that for convenience we are going to establish that I1 is going to be equal to I2. So what are we going to get if we do that? Well, the kinetic energy is going to be equal to 1/2 times I1 times, well, this quantity squared, which is going to be phi dot squared sine squared theta sine squared gamma plus 2 times phi dot sine theta sine gamma theta dot cosine gamma plus theta dot squared cosine squared gamma, and then plus phi dot squared sine squared theta cosine squared gamma minus 2 times phi dot sine theta cosine gamma theta dot sine gamma, and then plus theta dot squared sine squared gamma, and then a plus I3 phi dot cosine theta plus gamma dot squared. We are going to leave it as it is. So we can see easily that this element cancels this element, and if you see here, we have a common factor of phi dot squared plus sine squared theta, and then this multiplies sine squared gamma plus cosine squared gamma, so that is going to be equal to 1. And the same thing happens here with the theta dot squared common factor. So this is going to be the kinetic energy equal to 1/2 I1 times phi dot squared sine squared theta plus theta dot squared plus I3 phi dot cosine theta plus gamma dot squared, like this. Okay, perfect. This will be the final result of this lesson. It is the kinetic energy in terms of the Euler angles. Look that here, if we want to construct a Lagrangian, we can do it with this kinetic energy, and the generalized coordinates of the mechanical system now, well, they are phi, theta, and gamma. Okay, so if we take that Lagrangian into the Lagrange equations, then we are able to find the equations of motion of the rigid body. But for now, the important thing here is that, well, we are able to express that Lagrangian in terms of some new generalized coordinates that are the Euler angles. So for now, just for now, the course on rigid bodies is completed. This is the last lesson of the course of rigid bodies for now. So thank you so much for completing the course, and we'll keep working on some more courses on physics in the channel. So thank you so much.